Now, can anyone tell me what type of function is this? Perfect. It's radical because it has a radical on top of x. Can anyone give us what this function represents, or what is it? Of course, because it has x in the denominator. And Tim, did you get my note on the test?
Oh, yeah, I got that.
I wrote this on his test. You're killing me.
Spoiler alert. It's me.
Okay, so now here's an example of a function. Yes, why? Because the power is the variable, or the exponent is the variable. Yes, so this is an exponential function. Here's another exponential function. Can anyone identify the base of the first one? So this is also exponential. Can anyone identify the base of the first one? Can anyone identify the base of the second one? Good. Now, I have a couple of questions for you. 1 raised to the 5th power, and I would like you to tell me what that is. 0 raised to the 3rd, and I would like you to tell me what that is. And -4 raised to the 2nd power, and I would like you to tell me what that is. So, you're welcome. So, 1 to the 5th power, please. Excellent. 0 to the 3rd power, please.
0.
Right. -4 to the 2nd power, please. How much?
16.
Yes. Okay, very good. So this is indeed 1, and this is indeed 0, and this indeed is 16. However, these are not allowed for the exponential function. So the exponential function cannot have a base of 1, cannot have a base of 0, and cannot have a base that is negative. And the appropriate question here is, wait a minute, you just showed us that all these exist. How come that I cannot put them in the exponential function? So the reason is, its inverse will not exist. So these are not allowed, since the inverse of the exponential function will not exist. That's the reason, no other reason. So what can the base be? So let's call the base b. Can be two things. B can be greater than 1, so this is the base. We're not talking about the domain. We're not talking about the variable here. We're only talking about how we define the exponential function. So the base cannot be 0, cannot be 1, and that cannot be negative. So it can be, oops. In the other class, I'm using A because that's what it's in their book. In your book, I think it's B. Doesn't matter, it's not important. So the base, which is the base of the exponential function, can be a number greater than 1, not 1, or it can be a tiny number between 0 and 1. And these are two examples, the base 1/2 and the base 3. Okay. The function will have two different shapes. Do we know another function that has two different shapes? What is this?
Happy face.
X squared, happy. So x squared and negative x squared, right? Two shapes. Linear function, right? Or linear function. Same thing here. Two different shapes, but very different. Okay. So let's start by graphing. F of x equals 3 to the x. Good. talking about the base. I'm sorry, now we're talking about the exponent. I'm asking myself, I know there are functions that are not friendly, and I know one, which is the square root. Not friendly, because the quantity under the square root must be greater than or equal to. We've been talking about this for 3 months, right? The quantity under the square root must be greater than or equal to 0, of course. I cannot take the square root if it's not 0 or more, right? So the quantity under any square root has to be greater than or equal to 0, correct?
Yeah.
Good. What other function has restrictions from the previous test? Rational, awesome, because the denominator cannot be 0. Now, I'm asking myself, is this function going to join that list of functions with problems? So let's think. Can I raise 3 to 0? 1. Can I raise 3 to 2? Can I raise 3 to negative 1? 1 over 3. So what will be the domain of this function? Because I'm trying to graph it, and remember we always start with the domain. So what exactly? This is a friendly function. No problems. It does not give us any headaches. So negative infinity to infinity, and this is f of x. I'm going to pick few x values close to 0, like negative 2, negative 1, 0, 1, and 2. So let's see. I don't want to forget. Who came in? So you just came in, right? I didn't give this to you. Who else does not have this? Okay, Mom. So this is good. Hold on to them. For the next test, we're going to go over everything. Okay, so please plug in negative 2 and tell me what you get. Please plug in negative 2 and tell me what you get. 9. Is that true?
1 over 9.
Aha! 1 over 9, I agree with. Good. Please plug in negative 1. Very good. Please plug in 0. 1. Please plug in 1. Please plug in 2. Good. We have never done this before, and please do not repeat it for other functions. It works here. I'm going this way. 1, 3, 9, with 3, 27, with 4, 81, 729, 10,000. Where am I going? Very good. Now I'm going that way. 1 over 3, 1k divided by 9, 1k divided by 27, 1k divided by... Can I say I have a negative k?
0.
0. That I'm missing k, if you want, but no. Very good, 0. So what does this mean? And we learned in the previous chapter. As x approaches negative infinity, the function values get closer and closer, closer and closer to 0. What does that mean? Only at?
0.
Only at? Exactly. Y equals 0, horizontal asymptote at negative infinity only. Because on the other side, it blows up. Goes to positive infinity. Ready? So let's graph this function. When we graph functions with asymptotes, what do we have to do first? Yes. This is an overkill because this is y equals 0. Please give me the first ordered pair. The first ordered pair. The first ordered pair is negative 2, 1, 9. 1/9. The next ordered pair is negative 1, 1/3. The next one is 0, 1. The next one is 1, 3. And this is the graph of 3 to the x. Very unusual, very unique. We've never seen this before. This function has a horizontal asymptote on one side and it blows up on the other. So this is the graph of 3 to the x. Now if you ask me what can you say about this function, I can say a lot. Here's what I can say. It's a friendly function defined everywhere, but its range is awesome. The range is 0 to infinity. Thank you. So number 1, domain, all your numbers. Number 2, the range is 0 to infinity. Number 3, vertical asymptotes? None. It's defined everywhere. So we can have vertical asymptotes. Awesome. Thank you. Good. Horizontal asymptote. Yes. At negative infinity only. Number 4. X-intercept. X-intercept. None. 5. Y-intercept. Can anyone give it to us in an ordered pair? Very good. 0, 1. Number 6. Is this function increasing or decreasing on all its domain? Very good. Increasing on all its domain. Awesome. 7. Is it 1 to 1? By the horizontal line test. 1 to 1 by the horizontal line test. Number 8. Does it have an inverse function? It's 1 to 1, so it has an inverse function. Good. I want to graph the inverse function. When I want to graph the inverse function, what do I have to graph first? Before I graph the inverse function. What is this? Yes, which one? Exactly, because we know that the function and its inverse will have a graph. Those graphs are symmetric with respect to y equals x. We know that from chapter 2. Very good. So please give me a couple of points so I can graph the inverse. We don't even know what it is, but we can graph it. 9, 2, very good. 3, 1, very good. 1, 0, very good. One more? Yes, 1/3? Exactly. 1/3 negative 1. Here's the graph of F inverse. We don't even know what it is yet, but I know it's graph. What can you say about the F inverse? Is it a friendly function or not? Friendly meaning, you know what we said. We established that it's a friendly function if it's defined everywhere and no problems. Is this function defined everywhere? Does it go to the other side of the y-axis? Does it go to the other side of the y-axis? No. So what is its domain? It has to be the range of the inverse of the function itself, right? So if the exponential function is defined on all real numbers, what is its range again? Very good. F inverse will have domain remember how the inverse function look? Yes, 0 to infinity, and the range will be right. That's how the inverse function works. If I take negative infinity to positive infinity to 0 to infinity, then the new function, the inverse function, is defined on 0 to infinity and returns everything back, right? That's how the inverse function and the function work. Bless you. Right? Yes, Mark. Mark?
What question is number 6 answering? Function is increasing.
Increasing on all its domain.
Always.
Always increasing. Follow my hand for a moment.
Forever.
Yes, exactly. And I have students sometime in the middle of the semester, they ask me, can I still improve my grade and get an A and so on and so forth? My answer is yes. If your grade from now on will follow an exponential function with a base greater than 1, yes. Now you know what I'm talking about. Very good. So let's look at the other shape. Let's say f of x equals 1/2 to the x. Please give me the domain of this function. Very good. It's exponential. It's friendly like the polynomial functions. Very good. Let's choose the same numbers, -2, -1, 0, 1, and 2. Please plug in those numbers and give me the coordinates that I should plot. Yes, 4 indeed. Please plug in -1. Indeed. Please plug in 0. Very good. Please plug in 1. Very good. Please plug in 2.
1/4.
Very good. Awesome. Like before, and do not apply this procedure for other functions. From before, like polynomial and so on and so forth, we have different concepts, although for some of them will work. I'm going to go this way. 1k divided by 2 people, 1k divided by 4 people, 1k divided by 15 people, 1k divided by 100 people, 515 people, 1k divided by 1,000,000 people. How much will I give you?
Less than crumbs.
Less than crumbs, he says.
You don't want to play.
On the other side, 1, 2, 4, 8, 16, 32. Very good. What does this say about the graph?
It's going down.
This one. What does this say from the previous chapter about the graph?
There's a horizontal.
Very good. Horizontal asymptote at only. We've never seen this before, right? This is new. So I have to graph the asymptote first, although it's an overkill, is y equals 0. I don't really need to do this. Please give me some ordered pairs that I have to plot. Yes? Very good. Very good. Very good. Very good. And then I start getting in trouble because I can't plot those. Very good. So this is the graph of 1/2 to the x. Going back to this list, what will you say about the domain of this function? What will you say about the range of this function? What will you say about the horizontal asymptote? But only at positive infinity. What will you say about x-intercepts? What will you say about the y-intercept? What will you say about increasing or decreasing on all its domain? It's decreasing on all its domain. Look at my hand. Very good. And is it 1 to 1? Does it have an inverse? Very good. So give me points so that I can graph the inverse. So what do I have to graph first? Very good. Awesome. So give me a couple of points so I can graph the inverse function.
4,
2, 3, 4, -2. Awesome.
2, -1.
You said 2, -1? Yes, I'm sorry, I didn't hear. Sorry. Good.
0, 1.
Careful.
1, 0.
Correct. And remember, if this function crosses here, that is a point in which x and y are the same. So if you reverse them, that point has to belong to the inverse as well. We didn't have this here because this function did not cross y equals x. But this one crosses. So does the inverse. Because at that point, y equals x. And y equals x. So this is F inverse. What will you say about F inverse, especially the domain? The domain of F inverse is? So if the domain of the exponential function is this, and the range is this, so the domain of the domain and range for the inverse function, it has to be 0 to infinity. As you see, it's a vertical asymptote. This one has a horizontal asymptote. This one has a vertical. So 0 to infinity, which makes this inverse function a function from the category of non-friendly, because it's not defined everywhere. Okay, ready? So what have we learned so far? We've learned that there are two new functions, or basically one, but with two different shapes. If its base is greater than 1, it will be increasing on its domain with a horizontal asymptote here. If the base is less than 1, it will be decreasing with a horizontal asymptote here. Now my next question is, let's determine a function or create a function or look at a function with transformations. Okay, so I'm looking at problem 29, in which we have h of x equals 2 to x plus 1 minus 1. We are asked, so I'm helping here by choosing also to help you review everything. So we're asked to use transformations on this. First, I have to identify the base function. Can anyone tell us what is the base function used to create this? The base function. 2 is not a function. Say it again. Say it again. No, I just didn't hear.
Oh,
I want the base function for creating this. We have a list of functions that we know. If it's the square root, if it's the absolute value, if it's 1 over x, if it's x squared, if it's x cubed, if it's 2 to the x, if it's the cube root of x, if it's that's about it. Thank you. Of course, it's the exponential function with a base greater than 1, which is 2 to the x, which has, it's a pure exponential, no transformations. Awesome. Good. So then the first transformation is on the exponential function 2 to the x. That's what we are studying. We are studying exponential functions. Not 1, not 2, not minus 1, right? The chapter is on exponential functions. Good. What is the first transformation on 2 to the x? So just dictate so I can write it. Which one? Very good. What transformation is this on the base function? Depending on what I'm changing. If I'm changing x, no. If I'm changing y, yes. So if I'm changing x, I do this. If I'm changing y, I do this. Which one is it? Yes, I'm changing x. So if I'm changing x, then you have to say this, depending on which direction we're going. How many? That's it. 2. That's why we need to review. Good. And then there is a transformation on number 1, on this one. So I have to write 2 raised to x plus 1 minus 1, and it is indeed down 1. Do we agree? Yes? Okay. Now I'm asking myself, how do I graph 2 to the x? Is it an increasing function? Is it a decreasing function? Does it have asymptotes? How do I graph it? Yes, and it has a horizontal asymptote at negative infinity. So it's increasing, and it crosses the y-axis where? Look at the graph. We just graphed it with a different base. So where does it cross? Exactly. Very good. So this is 2 to the x, and it crosses at 0, 1. Awesome. Then you told me to shift this graph left 1. Here's my marker. Okay? My marker is this point right here. I'm shifting it left 1. It goes to negative 1, 1 right here. Agreed? This point moves here. So here's the new graph. Oops, I missed it, sorry. So this is 2 raised to x plus 1. Can you tell me the horizontal asymptote for these two graphs?
0.
Y equals 0 is the horizontal asymptote. Correct? Good. Now, you told me to shift this down 1. What do I have to shift first? Correct. And where does it go? From y equals 0 to? Very good. Excellent. So I have to draw a horizontal asymptote y equals negative 1. And my marker is this point again, right here. Where do I shift this point? From negative 1, 1 to? Negative 1, 0. Here it is. So this is the graph. I should have used a different color. Sorry about that. I don't know where it crosses the y-axis. I have no clue. But this is the graph or the shape of 2 to x plus 1 minus 1. Any questions? Any questions?
So if the base value is greater than 1,
Yes.
it's always going to be 1, 0.
Yeah, 0, 1.
0, 1, sorry.
Correct.
Yeah.
Because you plug in 0 for the power, and any base raised to 0 will be 1.
Gotcha. So we
Yes.
learned those two basic functions, and we add stuff onto it.
Right. But if you have to shift the graph,
Right.
if the exponential function is not the base pure exponential function, the x and y intercepts may be different, may exist, blah, 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 shifts left and right, down, up. So like here,
Yeah.
right? So the original function does not go below the x-axis. It's always positive.
Yeah.
But this function, 2 raised to x plus 1 minus 1, goes to below the x-axis because it's a shift, downshift of 1.
You'll still start at the same spot.
But I have to, yes, but I have to start with the base function always. Remember when we graphed the absolute value, we graphed the base function, and then we did whatever we wanted to do with it. The same with the square root, the same with all the others. Is that okay? Good. So now I would like to, the other functions, the other problems, 31, 35, 39. So they're only asking you to graph. I want to present two special graphs here. How special? Here they are. If you go to your calculator, they are so special that they have a special designated key in the graphing calculator. One of them is right here in blue, 10 to the x. with this second 10 to the x, let's say 5. And the second one is right here with e to the x. So let's say with the second key, the second power. Okay? So they are widely used in real life situations. One of them, the one with the base 10, is called common exponential function, and the other one appears in nature so much that it's called natural exponential function. So f of x equals 10 to the x. It has a special name, common exponential function. And the other one, f of x, is e to the x, and it's called natural exponential function. Yes, Mark?
Our book says y to the x. Is that the same as e to the x?
But is y or f the same or not?
No, but our book says when it refers to the natural exponential.
Right, so my question is f of x and y the same thing?
Yeah.
Of course, they are the same. We do not like to write, I don't want to ask you find y when x is this. I'm asking you find f of 3.
Okay.
Otherwise, I would have to say find y when x is 3. And then it will take longer.
I mean, they just refer to it as something else in the book. This is y of x, but e is x, e of x. So it's the
You
same
cannot
thing.
write, you cannot say y of x.
Well,
It
it looks
says,
just like the e to the x, put it to y instead, and then this says our book will find on our graphic calculator.
let me take a look. I mean, what is the difference? I'm not sure I understand what.
I just want to make sure that it's the same.
Application exercise should be
475. Okay.
just as easy. See, mine leave X key.
Here.
Yep.
Because there is no f of x in the graphing calculator. But what difference does it make?
I just want to make sure that it's the same, right?
The graphing calculator doesn't have f of x. It has y. It does not have f of x here.
Right, I understand that.
But they are the same. There's no difference between y and f of x. They're measured on the same axis.
Right,
They
I know that. But when the book says y of x is your button, and then that doesn't have the same button, I just want to make sure that it's the same.
But I'm not talking in terms of the calculator. I'm talking in terms of what you have to put on paper when you take a test.
Right, that will be the same.
Right. But in the graphing calculator, you cannot type in f of x.
That's why they give you a button. But your button is
But we're
different
not
than what
working
the
on the
book
y
says.
on the graphing calculator just yet.
We're on the same page.
Yeah.
Yeah.
Yeah, I'm sure we are. No questions asked here. Okay, so when the base is e, this is called natural exponential function. When the base is 10, it's common exponential function. And they also, when we get to their inverses, they will carry the name. So their inverses will have the inverse of this function when we get to it in a minute. This will be the common blah, 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 and the inverse for this will be the natural blah, blah, blah function. Okay, so I would like now to look at a couple of applications. Let's also graph this. Since you mentioned, let's graph both functions. Let's say 10 to the x. I could use actually this. I'm not going to use it. 10 to the x. And I could use the inverse function, b to the x. Now let's think for a moment. Do we expect the graph to be increasing on all its domain, or do we expect it to be decreasing on all its domain for e to the x and 10 to the x? Yes, because both of them have base greater than 1. It's not 0. We're not talking about 0, because remember, for the base between 0 and 1, the function is decreasing. We're not talking about 0. We're talking about greater than 1. If the base is greater than 1, the function is increasing. If the base is between 0 and 1, the function is decreasing. There is no base of 0, there is no base of 1, and there is no negative base. It doesn't exist. So when I go to Zoom 6, I know the calculator is lying, so this is 10 to the x, and here comes e to the x. Here it is. Of course, when x equals 1, e to the x is roughly 3, and 10 to the x is 10. So that's why 10 to the x grows faster than e to the x, and it's closer to the y-axis because it has a higher value. Yes, somebody was going to ask a question. I want to answer.
So what is e to the x again? You said e is what?
2.718. So here it is. Here's how you find what e is. So let's go to second, and the caret. No, not the caret, I'm sorry. Second and the division symbol. And then you press enter. And this is a number that is, the name of this number is Euler's number. He invented it, and he showed how useful it is in real life applications. So that's why it's I think it was Swiss. So this is Euler's number. Sorry, Euler's number, so E. So that's why it's E. They used a lowercase e standing for his name. Great mathematician.
Will that just repeat 18281? That would just like repeat to infinity or what?
Which one?
The e, because it shows 7 to 7.
It's an irrational number. It goes on forever.
So will it repeat the pattern, or is it just like random?
It does not repeat. It's irrational. Anything that repeats the pattern is rational.
Oh, yeah.
Everything that goes all over the place and it does not have a pattern is irrational. It's like pi. Pi is an irrational number. E is an irrational number. The square root of 2 is an irrational number. There is no pattern in it. Good. So now I would like to look at a couple of applications here. When we deposit money in a bank, or when we take a loan, the interest is compounded. No. When we deposit money, the interest is compounded. So compounded interest for deposit. Okay, so there are two possibilities for compounding interest. And yes, the formulas will be given to you. One is n times per year, and the other one continuous. The formula for getting the accumulated value, if the interest is compounded n times per year, is this. A equals P 1 plus R over n, lowercase n, raised to n times t. I'll explain what each portion represents. P 1 plus R over n, and the power is nt. For continuous compound interest is A equals P times E raised to RT. So now let's work with each and every one of them.